Good morning, Vamsi sir. Vamshi sir, are you able to hear me? Good morning, Vamsi sir. Are you able to hear me? Sir, am I audible? Good morning, Vamsi sir. Sir, am I audible? Good morning, sir. Vamsi sir. Sir, can you unmute your mic?
സാറടുത്ത് പറഞ്ഞോ? ആമാ സാർ പറഞ്ഞോ. അത് സാർ 10 മണിക്ക് വേണ്ടി.
Hello.
Hello, sir. Good morning, sir. Vamsi, sir, good morning.
Hello.
Yeah, sir. Are you able to hear me? Vamsi, sir. Are you able to hear me?
Am I audible, sir?
Yes, sir. Sir, you're audible. Sir, are you able to hear me,
Hello?
Vamsi, sir? Good morning, Vamsi, sir.
Good morning, sir. Good morning, Vamsi, sir.
Hello, sir. Dr. Sudhakar, sir. Very happy to see you. Dr. Vamsi, HOD, all others, good morning.
Good morning, sir. Good morning, sir. Good morning, Raghavan, sir. Sir, good morning, respected Raghavan, sir. Vamsi, sir.
Coordinator, you're all fortunate that second day also we have Dr. Sudhakar Rao, sir.
Okay. Sudhara, sir. Welcome, sir. Good morning. Welcome, sir.
Hello. Hello.
Vamsi, sir.
Yes, madam. Good, madam.
Sir, you're able to hear me?
Yeah, I'm hearing you, madam. Are you able to hear?
Okay. Yes, sir. Yes, sir. Now it's good.
Shall I just test the screen sharing, madam? Once.
Yeah, sure, sir.
Vamsi, sir.
Yes, sir.
Our beloved Raghavan, sir, is in this program, as well as most respected Sudhakar Rao, sir, is also here.
Oh, yes, sir. Sir, I'm very happy, sir. Thank you very much. And very good morning to all, sir.
Welcome.
Good morning to you.
So, good morning, Raghavan, sir, and Sudhakar, sir.
Yes, sir. Good morning.
Morning.
Vamsi, sir, shall we try sharing the screen? Yeah.
Sir, respected Sudhakar Rao, sir.
Hello.
Sir, very good morning to you, sir. Very good morning.
Good morning.
We are very happy that, sir, you are being this part of this STTP, sir. And today also you are here. And we are very, very much proud about this.
Yeah, you're making me learn something. So I don't want to miss it.
Sorry, sir.
Hello. See the screen, madam?
Sir, we're able to see the. Are you attending from the over phone, sir? Yeah, now it's good. I can see the slides. I can see the slides, sir. Now it's good.
Okay, I'll just see the variation. Is it good, madam?
Yeah, it is good. It is good, sir.
Okay.
Okay. So we'll start in another 7 minutes, sir.
Sure, madam.
Okay.
Yeah. Okay.
Respected sir, Dr. Sudhakar, do you know the result, sir?
No, I didn't find out, but
Okay. I think he has got 50% chances.
Yeah, I think it's between the two. Ray Lu and him. So depends. Pretty close.
Many of the slides what he present, I have seen you both together.
I just got the email. So Ray Lu won the election.
Okay.
So Ray Lu has 21,120 votes.
Okay.
Saifur Rahman got 15,781 votes. And Ramesh got 12,852 votes. I think
how
he
much,
got
sir? Ramesh, how much, sir?
12,852.
Okay.
And also there is Region 10 election also. Let me see.
This is our ISRO person. Did he get, sir? Ahmedabad ISRO person.
No, this is Region 10 IEEE level. So
Okay.
who got was Chunchi Lance, 5,686 votes. There's one guy from Supavadi Rambit. I don't know. He looks like a Celanese name. Celia Shahnaj, I think she lost.
I have seen many of the programs of Dr. S.K. Ramesh. The slides showing you both together. I think many common functions you both attended, I think.
Not many, some maybe.
At least 3-4 slides I have seen.
Oh, okay. But Ray Lu has, I think, bigger.
You know her, sir, personally?
Ray Lu, him? Yeah, I know Ray Lu as well. Yeah.
Where is that person now, sir? Where is
Ray Lu is from the East Coast, I think North Carolina or someplace.
Oh. HOD madam?
Yes, sir.
After the FDP is over, you should have contact with the greatest IEEE fellow,
Yes.
Dr. Sudhakar Rao sir.
Yes,
and make use of the best opportunity.
Sure. Principal has already told me. She reminded me yesterday evening also.
He's one of the top 10 in the world.
No.
That is what we consider, sir, really.
No.
Sure, sir. We'll surely keep in touch, sir.
No exaggeration. We were longing whether he will come for 1 hour for our FDP.
Yeah.
So we are all very fortunate.
That's very clear. That it is an odd timing over there. So he's actually, it's a great honor. As Perumal sir said, it's a great honor that he's joining for this.
Sometimes he gets up at 4 o'clock or late night. That shows his interest.
I'm older than you, Professor Raghavan. So
really, sir?
I'm older than you, so old people cannot sleep. So
I am thinking that you are younger than me.
No. I saw your resume. I'm older than you. Which year you graduated?
I'm 66.5.
Oh no, you're young boy compared to me.
Very, very happy. While Ramesh news is bad for me, this news is good for me.
Good morning, sir. Mahadevan here.
Hello, sir. Good morning, sir.
Good morning.
Welcome, Mahadevan, sir.
Mahadevan, how are you?
Good morning, Dr. Sudhakar Rao and
You look
Professor
more
Raghavan and
colorful.
all, Perumal, Shankar and others. So today's this thing by Dr. Vamshi.
Sir, you know him, sir?
Sir, good morning, sir.
Actually, he had not joined when we were there. Okay, he has joined later. He is much younger person.
Yes.
So
Yes,
anyway,
sir.
this is one area where we have almost we have excelled, because almost every requirement of filters for spacecraft has been done by indigenously. So
Yes, sir. Yes.
because that is a very major part in the full spacecraft, as everybody knows. So and every spacecraft, every system requires a special filter.
Yes,
So it has to be done so very meticulous. So we have to keep some people exclusively for this job.
yes.
So
Sir, good morning, sir.
I'm happy that filter is included along with this major this thing, which is required immediately after the antenna.
Yes, sir.
Thank you.
Mahadevan, sir.
Yeah.
Good morning, sir. I'm Vamsi Krishna.
Where is Vamsi? Where are you? I'm not able to see you.
Sir, just I am attending from my mobile, sir. Now I'm sharing the screen. So that's why
Yeah.
I'm not
Oh,
able
you are
to.
sharing the screen, is it?
Yes,
So how are you doing? Fine.
yes, sir. We are very kind, sir.
So we are
Sir.
all very much excited to hear from you.
Oh, thank you, sir.
So
Yes.
that's a great thing.
Yes.
I think, and you got stalwarts really listening
Yes,
to your
sir, yes.
lectures. Huh?
Yes, sir. I'm so happy and excited, sir.
Yeah, very, very nice. And wish you all the very best. Okay.
Thank you, sir. Yes,
Right.
sir. Thank you.
A very good morning to everyone, and a warm welcome to the second day deliberations of Phase 3 AICT sponsored 6-day short-term training program on the topic Trends and Technologies of Antenna Design and its Research Scopes. It's a great privilege for us, the faculty of the Department of Electronics of Kochi Institute of Science and Technology, to host this program. Let's move on to the first technical session of the day on the topic Transmission Line, RF Microwave Filters and Application to Antennas and RF Front End by Dr. Vamsi Krishna Velidi. Dr. Vamsi Krishna Velidi is currently working as a scientist in Antenna and Passive Systems Division, Communication Systems Group at UR Rao Satellite Center, ISRO, Bangalore. Sir received his MTech and PhD degrees in RF and Microwave Engineering from the Indian Institute of Technology, Kharagpur. Sir joined the ISRO in 2011, where he is actively involved in the design and development of miniaturized high-performance RF and microwave passive systems for various spacecraft and ground applications. He has authored and co-authored more than 50 research publications that include 27 in international journals till date. Sir is a recipient of ISRO ASI Young Scientist Award for the year 2016, ISRO Team Excellence Award 2017, and was awarded first position in URSI Regional Conference on Radio Science 2017 Young Scientist Award competition. He is a senior member of IEEE, and also during the year 2015 to 18, he has served as the editorial board member for Wiley International Journal of RF and Microwave Computer-Aided Engineering. His current research interests include design, analysis, and characterization of high-performance compact passive RF and microwave integrated circuit components using planar substrate integrated waveguide, semiconductor technologies, and millimeter wave applications. We are very excited to have you, sir, for our STTP program, and I kindly invite you to drive the session. Over to you, sir. Vamsi, sir?
Hello?
Yes, sir?
Are you able to hear, madam?
Yes, sir. It's good. Sir,
The
we're
screen
not
is
able
showing.
to see the slide Um, I think it's getting loaded.
Now, madam?
It's just a blank screen now, sir. It might take another, I mean, it might take more time. I just can see a white screen. I'm not
Ah,
able to see the PPT.
okay, madam. 1 minute.
Now it's good, sir.
So
Now it's
previously
good.
it was seen, no, madam?
Yeah.
Yeah, yeah.
Now
Now
it's
I'll
good,
go ahead,
sir.
madam. Yeah. Okay, madam.
Over
So a
to you,
very
sir.
good morning to all. Thank you, madam. Yes, madam. Thank you very much for the nice introduction, madam. So very good morning to all. Hello. Am I audible, madam? Just
Yes,
confirm, please.
sir. It's very clear, sir. It's very clear. And the slides are
Sure.
also
Okay,
good.
okay, okay.
Okay.
Okay, madam. Thank you, madam. And very good morning to all. I'm very happy and excited to present my presentation in front of the world-class top in our research. There, I mean, our gods. I can feel where we draw the inspiration. So I'm very happy to present in front of all of them. So now this talk actually mostly focus on microwave filter, but I'll give a little introduction before entering into particular topic. Just to get into this field, so where there is some fear for the area, particularly RF and microwave engineering, and in particular to the passive component design or antenna design. So always electromagnetic field theory, all people will get little scared. So the main motto of this presentation is to open up a new area where the field interaction, the field theory comes later. First, understanding components, which is pretty easy and interesting also. If there are the basic concepts of transmission line theory, so then people start understanding the individual element behavior, and so everything they can derive by their own mathematical analysis, so that they by their own process like MATLAB. So no need to depend on any simulator. So, madam,
Dear
hello.
participants, kindly please mute your mics.
Can somebody mute?
Yes, sir. So just a minute, sir. Just a minute. Yeah, now he have muted it. Now it's good, sir.
Sure. Yeah, 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 yeah. So that is motivation of this area. So now I'll give a try to the maximum extent how best the student get interest in this area. So the ultimate goal is to design planar passive components or any technology that comes later, because the most of the circuits what I explained is based on the circuit theory. So finally, ultimately, the realized component will be of smaller size to meet the goals of the present scenario, and that is easier to realize. But it should be cost effective, and that must have superior characteristics that should meet the present stringent requirements. So, obviously the applications are the present day most miniaturized or cell phones and WLL and wireless LAN applications and ultra wideband and particularly satellite communication systems also. As we are moving for higher and higher frequencies, always we should think about one step ahead for the next application. And coming to the academic point of view, the most motivation is to get a publication. So whatever existing in the literature, if we give one step an advanced version or any performance improvement also we consider the publication. That is motivation for researcher before getting industry application, because not easy to get action with our industry. So the motivation is publication only. We'll see what is the current topic published. So we'll get to know what are the applications also, and we'll start thinking give a better performance than that, so that we'll get one more application. So we get to know the methods also. So these are the highly reputed journals in this particular microfilter area. So that top one is the entity and my wireless component data, MOTL, RF connectors. These are the journals. Now the presentation outline. So first we'll give the introduction about the micro task components. So what are the importance and where these are crucial in any communication system, and what are objectives and what is the overview of the workflow. So starting from the specification for the designer and ending analysis application and what is the workflow. And here mostly we are focusing on transmission of the filters. The brief knowledge about the transmission theory will give. So what are the building blocks to construct the filter we are going to explain. And the filter based on the transmission line method. So there are variety of filters for particular applications, band stop, low pass. And nowadays the multi-band filters are of great importance. So that I'll explain what is the application of the dual band filters. So similarly, band pass filters also and their dual band application. And after that, as I mentioned, these filter applications mainly focus for antennas in terms of filtering antennas. And one more antenna application also. And for the R content, dipole is a crucial element. So for that, any trans receiver, which is something both transmitter receiver, and they are sharing a common antenna, then how these filters are playing major role in the dipole design. And apart from that, there are other components also. They are used for the anti-feed network. Those are hybrid couplers for variety of functions like to get circular polarization or for feeding a multi-array. So then how these filtering concepts can be applied to those hybrid couplers so that they will get miniaturized and at the same time they will get superior characteristics in terms of their out-of-band harmonic suppression. If that components are used for antenna feed, so that the overall performance of antenna also gets improved. So these are the applications I am going to in this presentation. Now coming to the introduction of the components, mostly important textbooks are the POSA. That is the best book to understand comfortably the component as a very good book. After there are several, I am not comparing everyone. So for a beginner, my experience is the best one is the POSA. And particular to RF design, this last book is very strong. It is now
Vamsi
updated
sir,
version also there.
Vamsi sir, sir, may
Yes,
I
madam.
interrupt you, sir? The voice is breaking,
Yes,
sir.
madam.
Voice is breaking a bit.
Okay, madam. Now, madam.
Now it's good, sir. Now it's good.
Hello. Now it's okay. Yeah. Okay. Yeah. So that the last book is about those who are particularly interested about filter. This is the book covering almost every technology. Yes. Now for the passive components, these filters cover balance are the crucial components in transition. And finally, the planar technology compared to other technologies, these are bit preferred because of the fabrication cost and they can be easily printed using PCB technology. And commercial application low cost and and depending on the performance, we'll choose a particular technology. But what a transmission line theory we are going to discuss, these can be readily converted in planar technology. So, and obviously we know the advantage of microchip in among the all planar components. Microchip is a bit easier with the high density packing, and we can include other like chip components also. So, and integration point of microchip is relatively better than our strip line and suspended strip line and other technologies. So, coming to the filter, those are the most important components for any communication system. As a communication system consisting of transmitter, receiver, and antenna. So, all the systems almost are used without the filter. I can say because the filter is discriminating component for a dense, high frequency electromagnetic spectrum. Because the whole spectrum is fully used for different applications for different bands. So how to separate out the band so that the particular transmitter will receive only particular frequency. So the filters are indispensable components, I can say. Coming to particular transmitter and receiver. If it is a receiver, there are several places where the filters are crucial. That is first and foremost one followed by antenna is the filter only. Because though antenna receives a particular narrow band signal, there are out of band lot of noise also included in that. So that filter should suppress all the noise and only pass a particular frequency. So that is called pre-selection in the receiver. So this filter should be of low loss with high rejection in the outer band, and it should be narrow band particular to as per the requirement of the receiver. So this is a challenge for the designer because high rejection and low loss is a bit challenge for the designer.
Vamsi, I think you are breaking up.
And after that,
Hello?
there are
Vamsi, I think you are breaking up. We can't
yes,
hear you properly. Can you log in
just
through
a
the
second.
computer?
Now I'll move it.
I think you logged in through cell phone.
Sir, actually, I have desktop, sir. That is a problem. So now is it okay, sir?
It's
Sometimes signal get cut.
it's intermittent, so can't hear properly.
I think Vamshi, you should keep the
So I moved.
this thing close to your mouth.
Now is it okay?
Keep the mobile close to your mouth so that it doesn't get disturbed so much.
Yes. Yes, sir. Yes, sir. Now I'm holding the microphone close to. Now is it okay, sir? Hello?
Still not clear.
Yeah, I think it's
Hello?
better. It's better now.
Sir, are you using the
Okay, sir.
headphone?
With this,
Sir?
I'll.
I think you are using the headphone, sir.
Yes, sir. Phone. Hello?
Yes, sir. Vamsi, sir.
Now shall I proceed, madam? Is it okay?
Now it, yes,
Yes,
sir.
madam. Is it
Now
okay,
it-
madam, now?
It is good now, sir. In between, it was breaking.
Okay, madam.
Okay.
Okay, madam. Okay. Please tell me, madam, whenever it is breaking, I'll correct it. I'll change my position.
Sure, sir.
So, yes. So, apart from that, there is one more place that is called intermediate frequency, because before mixing, only an image frequency that produces higher receiver. So, it is crucial to reject the frequency also. So, again, there is a requirement for filter. So, like this, after down conversion also, at low frequencies also, we'll need to use some filters. So, in the receiver itself, starting from high frequency signal filter at preset stage, after down conversion low frequency filter. So, variety of filters will be used in the receiver depending on the frequency of application. So, starting because of the low loss and high rejection, waveguide at stages like low frequency rejection, we can use microstrip filters comfortably that will meet the specification. And after further down conversions, we may need to go filters or crystal filters. So a receiver is a subsystem, I can say, where all variety of filters will be used. At the same time, for the transmitter, there are some intermodulation components for the components and some harmonics also for the high power amplifiers will be generated. Those are all to be suppressed before transmitting. So that as output, even at carrier generation stages also, variety of filters are required for the transmitter. And coming to other hybrid passive components, these among several hybrid components, hybrid power divider, the branch line coupler and rat race coupler called as quadrature hybrid and other one called as 180-degree hybrid. These are the very popular used for different phase because where the phase requirements are there. So these components also, particularly at low frequencies, they will fail. And these will also have some harmonic components at multiples of odd multiples of the frequency. So these are to be suppressed. So the filtering concepts can be used to design these hybrids also. So this I will show in the application part. And a balun is also a component where the differential components are much used, where that requires 0 and 180 degree phase. For the purpose, balun is used. And for antenna like dipole applications and other applications, this balun is the first component. So to miniaturize artifacts like to suppress the and harmonics, and also this balun can be constructed using filtering concepts. So, so design objects I'll explain for the filters compared to the ideal response and conventional response and the present performance response. These, if you get a clear understanding about the responses, then we'll concentrate on how to generate these responses using methods. The first one is suppose band stop filter. As we all know, the response consisting of pass band and stop band were particularly required. And again, it follows another pass band. Now, the conventional transmission filter that will give a stop band with a narrow band as shown in the first figure. And now, if you see the pass band to stop band transition is gradual. If the bandwidth increases also, as we have to increase the bandwidth means we need to increase the filter order. And the design of the present challenge is without using the filter order, if minimum number of components can be used in the topology so that performance increases drastically. So the bottom figure, last figure we'll see, it is having 3 transmission zeros compared to the conventional design. So here, obviously the bandwidth got almost, it is multiplied by several times. At the same time, the pass band to stop band transition became very sharp. So these type of filters are highly required for the present communication system. And here I am showing the out of band responses. If the design frequency is at 1 GHz, suppose, if we see at odd multiples because of the transmission periodicity, we'll get harmonic components odd multiples of the frequency like 3 and 5 and 10, 9. So these are the if you are able to design a pass a fundamental component remain unaffected, and if you suppress these harmonics, that is also one of the good research topic. And this dual band filter response I am showing, this is dual band stop filter. So we should not get confused the multiple bands harmonics. Here the two bands are controllable depending on the topology. At the same time, the whole set will repeat at odd multiples of frequency. So these are harmonic sets we can say for the dual band filter. And the low filter, and conventional methods we see a grand roll off from the pass stop band, and the stop band bit also somewhat extra to some extent. Now the present what the design goal is to increase the selectivity of the at the same time you are able to suppress as much as right in the band, like up to now present day research is up to 10 times the cutoff frequency also filters are available. That is the low pass filter
Vamsi, sir.
up to 10 times the cutoff frequency.
Vamsi, sir.
So if you
Vamsi,
see
sir.
band filter with wide stop band can also be thought as a low pass filter.
Vamsi, sir.
Now coming to the band pass. Yes, madam.
Sorry
Yes,
to
madam.
interrupt you, sir. Sir, the voice is
Is
breaking.
it okay, madam? Like in problem?
Sir, the voice is not going smooth, sir. It's breaking in between.
Okay.
Sir, it is a nice lecture.
Okay, madam. Now
Sorry. Everybody is
maybe
interesting.
sometime-
Everybody is interesting, sir. Please check.
actually because of some maybe connectivity issues in signal Sometimes it is good news, sir, at some point.
Sir, will you please shift it to the computer, sir, laptop?
Sorry to say, sir, I don't have now right now laptop.
Okay, okay, sir.
So
Okay, sir.
I'm in office actually.
Okay, okay, sir. Okay, sir. Thank you.
Actually, this is the only way. Sorry for everybody because uh, I think it gets clear after some time. Now,
Sir, now it is very clear,
hello.
sir. So can you try talking like this? Now it is very clear. But
Madam,
after some
maybe
time.
some.
Hello?
Okay, madam, I'll be in this position now. Okay, madam. Yes, madam. Yes, madam. I'll be in this position.
Okay, sir.
Hello.
Yes, sir. Okay.
Hello.
Hello, sir. I'm able to
Shall I
hear you.
proceed, madam?
Yes, please proceed, sir. Please proceed.
Yeah. Okay. Okay. Okay, madam. So just now for this band pass filter, if you see the conventional filter using band of 4 steps, now I'm going to show that there is a pass band simply at upper frequency. And now the present research, if you see, the first transmission geos are of great importance because as many as transmission filters in the outer band, the filter activity increases. So compared to 1 second, the lobes are sharp. And similarly, related to the harmonic rest, so this same these high performance transmitters also with repeated their respective multiples. Similarly, dual band pass filter. So here pass bands. So these are now presently of great use for the mobile bands like GSM. If you see, take at 0.9 GHz and 1.8 GHz, 0.1 GHz. So here, instead of using two filters for the two frequencies, a single filter in the two bands simultaneously is very important. So how to design these filters and what are the methods? What is the understanding to get this type of response? We are going to show. Now just I'm showing all the responses of it. At one up to 10 gigahertz of hybrid coupler response is shown. There are and the filtering cons, applying filtering cons to the hybrid coupler. All harmonics up to 10 times the operating fundamental frequency all got suppressed.
Vamsi,
These
sir.
are
Vamsi, sir. Vamsi,
important.
sir. Sir.
Yes, ma'am.
Mahadevan
Yes,
sir is telling
ma'am.
it might be better if you could log off and log in again. It might improve
Sure, ma'am. Sure.
the voice
I'll do.
clarity. Can you log off and log in?
Sure, sure.
Okay, we'll
Okay.
wait, sir. We'll wait.
Okay, ma'am. Sorry for that. Fine.
No
Okay.
problem, sir. Yeah.
Fine, fine.
Madam, is he logging off and coming back again?
Yes, sir. He's logging off, sir. He'll join us shortly, sir.
Hello?
Hello.
Hello? Yes,
Yes,
madam. Is
Vamsi,
it
sir.
good, madam? No?
It is good, sir. Now we are able to hear you, sir.
Yeah. Okay, madam. So now this hybrid
Sir, the
coupler just
slide
I
is
am
not
discussing.
shared. Sir, you haven't shared the slide.
I share. Yeah. Now is it seen, madam?
Yes, sir.
Yeah, okay. So just now I'm discussing about the out-of-band responses for the hybrid couplers. As an example, I'm showing one hybrid coupler. As we all know, at fundamental frequency, we'll have a very good return loss and isolation, and at the same time, 3 dB division will be there. But whereas in the out-of-band, the same responses will be repeating. So after applying filtering concepts, we can suppress those harmonics as shown in the last diagram. So up to 10 times there is no harmonic at all except for the fundamental frequency. Now the workflow for this component design, just in advance itself I am showing. So whatever may be the partial component specification you will get, take the problem statement. And according to that, the main motivation first, where we get more information is the literature survey only. So we'll have some good literature survey. And so that we can understand what are the methods, what can be easily applied, and select any of that one. And theoretical analysis, suppose any transmission line based model is we take, so we can have the theoretical analysis. Now for that we need to perform a simulation. So if we have our own theoretical analysis for the S parameters, we can just write that small expression in MATLAB, we can get our own response. Or there are some commercial available EM simulators where the circuit simulation part is given, like ANSOF Designer or ADS. We can have ideal circuit component, transmission and elements, we can take and simulate. So we can compare these, whether this is meeting our specifications or not. Next, just particular technology, suppose microchip is selected, then convert all the parameters in terms of physical dimensions and construct the geometry. Then we need to have EM simulator here. So we'll implement the whole structure for the electromagnetic effect. So to see all the full wave analysis. So we can use any commercially electromagnetic available EM simulator. Then compare the results with our circuit simulation results. So there are several parameters which will deviate from the ideal response, because from loss point of view or substrate parameters and radiation effect, all will be taken care in your EM simulation. So finally, ultimately, we'll compare with our circuit simulation results. So how best these two are closer to it. Once these two are in good agreement, we'll go for fabrication and machining. So we have to just little bit understand the EM simulator also to how effectively use. Otherwise, we'll end up there only. We'll not get proper response. So that part is later. First, to get the understanding about the component before playing in just like that in electromagnetic simulator. If you have understanding with the transmission line theory, then we'll be more confident. So the main motivation for the lecture is that only. Now let us start the transmission line theory based filters, which are the building blocks for constructing any of the filter, like band pass filter, band stop filter, low pass filter. So just I'll give one slide presentation for how a general theory for the filter design. So this is based on several methods are there, theoretical, textbook methods like image parameter method, constant K derived, composite filter, Butterworth, Chebyshev. So where the first basic procedure is to get a low pass prototype. There are some tables given for the ripple, rejection, bandwidth, everything. So we'll select the component values for the low pass prototype. After that, there are some conversion methods that just will transform this into the required band pass or band stop filters. So this is the traditional way of doing filters. But now there are other methods also. This is just I'm giving the introduction. Now we'll see the transmission line based design. For that, a small understanding about the transmission line terminology is very much essential. So everything I'm not covering here. What are the major ones required specific to the filter design? Now I'll highlight those. So for any transmission line, we'll have two parameters to define. That is, one is impedance and its electrical length. So there is a relation between electrical length and physical length in terms of the propagation constant. Suppose we are talking in terms of lambda. Suppose the length is lambda by 2 or lambda by 4. So we'll have a conversion here. If it is a quarter wave length line, the corresponding electrical length, if you calculate, it will become 90 degree. That means a lambda by 4 line means 90 degree electrical length. Right? Similarly, half wave length means 180 degree. And the input impedance expression for any transmission line having a load is shown in the top. Now, there are some more prerequisite for understanding is that two-port network concept. So this you can get from any POSAR or any other textbook. There are some parameters to represent the network or to derive the final parameters which we are interested, like S parameters. We'll have some impedance parameters, admittance parameters, and ABCD parameters, and finally the S parameters. So we'll have this basic understanding in any graduation course. That's why take it for granted. I'm moving ahead. So these are the S parameters, and the terminology is what is the insertion loss, return loss for the filter, or if it is antenna, it's return loss. So after that, ABCD parameters for some are ready-made available in the textbook. Suppose if it is a series element, what are the ABCD parameters? If it is shunt element, if it is a simple transmission line, so the third one is shown, the transmission line what I have shown before. So the ABCD parameters are derived, and if any two-port network can be represented with pi type of pi configuration or T configuration, so that these will be helpful in your own derivation. So for that, just I am showing what is available in POSA. After that, in the derivation process also, you may require some conversion from ABCD parameters to S parameters. Suppose in a circuit topology, if it is easy to use Y parameters, if two circuits are in parallel, you can have the overall Y parameters by adding the simple individual Y parameters. Once you get the overall Y parameters, you have to convert into finally S parameters. So ultimately, the goal is to derive S parameters that is easy to analyze, and for measurement also it is easy to measure using any vector network analyzer. So for that, these are the conversion formulas available in POSA. Now coming to the basic transmission line elements. Here I have shown most of the popular elements. These are enough to construct any variety of filter. So the first one is simple transmission line with Z theta. It is in a normal transmission line. Now coming vertically, open-ended stub unit I have shown. That means the transmission line is connected in such a way that other end is simply left open. And if it is short circuited, and if two units are cascaded in the double section or triple section or four sections, that means it is called stepped impedance. Instead of single impedance, two impedances and two different electrical lengths we can use our same electrical length. And there are another class of transmission lines that is called coupled lines, where two lines are closely spaced. So this coupled line is one of the crucial element in band pass filter design, and similarly band stop also, so that we can easily get the band pass response. And variety of coupled line configuration, like other two ends are short circuited, one is open, one is short. There are 8 varieties that is also given in POSAR for reference. So these will be used as the construction elements for the filter. So the combination of these designs will do very interesting filter characteristics. Now, to understand the behavior of each and every element, I have shown some examples here. Starting from the first simple transmission line, no need to explain. It is a all pass response. Like if it is in terms of filter, it will pass everything. So instead of that, just I am starting with the open-ended line response. Now, if you derive its input impedance, taking from if you take the input impedance expression, just it is open-ended line. That's why load impedance, if you substitute ZL is equal to infinite in the above equation, we will get Zin is equal to minus JZ not cot beta L. Now this Zin, if you now first of all, to get this S parameters directly I have shown, first we need to get the ABCD parameters for this. So I'm going back to the slide. So now here the second one we can select, because it is a shunt element. Why it is shown? So ABCD parameters are 1, 0, Y, 1. So in place of Y, we need to substitute this Zin. That means 1 by Zin becomes the Y. So if you substitute there in the ABCD parameters, after that using the conversion formulas, you can write your code for S parameters. Now the S21 response I am plotting. So this is the way how to generate our S parameters. Once S parameter response is shown, now we can start understanding the behavior of the open circuited stub. Since if it is quarter wavelength, If you substitute beta in place of beta L, if it is pi by 2, 90 degree as we shown previously, then you will have a fundamental resonance at operating frequency. So the horizontal scale I have taken as 1 gigahertz. It can be normalized also, any frequency. Now, if we see the behavior, since electrical length is fixed, the operating frequency is fixed, but the bandwidth varies with the impedance. So if you see the profile, as the impedance decreases, that means if you convert into microstrip formula, if anybody is having some understanding, as the impedance decreases, the line width increases in microstrip. That way, just I'm correlating here itself. So at the larger line width, it is more capacitive in nature. So finally, its bandwidth gets increased. Now, what happens if it is a half wavelength line? So if you substitute beta L as 180 degree, then we are seeing two stop bands just with respect to the center frequency, like 1 gigahertz. So whatever I am saying, electrical length, all are at 1 gigahertz only. That is our reference frequency. If it is a quarter wavelength line, we are getting a straightforward stop band at 1 gigahertz itself. If it is a half wavelength open stub, we are getting two stop bands because the same stub becomes quarter wavelength at 0.5 gigahertz. And at 3 times of that one, 270 degree also, it is a periodicity, we'll see another stop band. So we can say dual stop band response, but at fixed frequencies are obtained when the length is 180 degree. The same impedance profile also will be applied here. So that is the behavior of the open-ended stub. So based on the length and impedances. Now the response of the short-circuited stub I am showing here. So if you substitute ZL is equal to 0 because the load as a 0 short circuit, then we will get Zin is JZ0 tan beta L. Then we'll have, if it is quarter wavelength, we'll get a pass band response. And here compared to the short circuit, open circuited stub, the behavior is little different because as the impedance increases, there the stop band bandwidth increased. Here as the impedance increases, the stop band bandwidth is getting increased. Now again, if you correlate with the microstrip, as the impedance increases, the line width becomes thin. So the thinner line with short circuited will have quite larger bandwidth compared to some thicker line. And suppose if the same short circuited stub is having 180 degree length, we'll see two pass bands at 0.5 gigahertz and 1.5 gigahertz, or if it is normalized, it is 0.5 to 1.5. So that is the behavior of a short circuited stub. So if it is quarter wavelength, we are getting single band response in either cases. If it is half wavelength, we are getting dual band type response. Now the other stub, that is called stepped impedance line. Earlier I have shown it again, it is an open-ended stub. Earlier in our previous slide, in the second graph, I have shown for the 180 degree open stub is having two fixed responses at 0.5 and 1.5. Whereas if you have split into two with different impedances, so that the theta 1, theta 2 are shown here, if we derive the expression, we will get the Zin impedance is like this. Then if you see the behavior, here depending on the impedance selection for Z1 and Z2, we are getting the controllability of the stop band compared to the single uniform impedance line. So here what is the observation is, if the impedance ratio is small, we are getting the two stop bands, the brown color graphs are shown. Those are moving away from 1 gigahertz. Always take 1 gigahertz is the reference. And if the impedance ratio Z2 by Z1 is higher, then we are getting the two stop bands like black color one. Those are coming closer. If it is 3, 4, like that, it will come close to 1 gigahertz. So like that, we can make use of this advantage of splitting the impedances into two. So these will be used in band pass filter response with wider stop band, wider pass band, or dual band stops with controllable bandwidth, just by controlling the impedances. So here, the basic understanding is, it is not a parametric based method. Suppose take any other structure, just varying the width and length, what is happening and all. It is not random. Everything is predicted here. We can have our predicted response so that comfortably where we want to exactly locate the stop band or pass band bandwidth, we can select based on the impedance selection simply. And now this is the response for coupled line. A coupled line, one example is shown. A couple line basically with two open ends will give a pass band response. And depending on the ratio of the, because a couple line can be defined using two impedances, that is called even mode impedance and odd mode impedance. Whereas for simple transmission line, it is simple impedance. And here also, like electrical length also, we should have even mode electrical length and odd mode electrical length. But we'll assume the phase velocities are equal in the two lines, so that we can assume the even mode odd mode electrical length as same single theta. So for a quarter wavelength, this type of open-ended coupled line will give a pass band response. And as the impedance ratio increases, like ZOE by that even mode odd mode impedance ratio, the pass band width increases. Accordingly, return loss also there will be a variation that we can see. We can here in the Mathai textbook, there are all variety of coupled lines and their ABCD parameters, Y parameters are well nicely given. So anybody can take from there and we can start using in your derivation. Now, using these elements, just first let us start with a band stop or low pass filter as an example. Now, as I have shown, for a single quarter wavelength open stub gives a stop band response. Now I'm comparing both the stepped impedance response advantage I'm showing. So the bottom figure, the stepped impedance line response is shown in black color. So where based on the impedance ratio, if it is Z1 is equal to Z2, fixed responses at 0.5, 1.5, it is greater or less than are shown. Now let us use this in dual band stop response. So this is a simple behavior. So finally, to get the transmission zero position, what to do is we should make the Zin is equal to 0. Then we'll get a condition in terms of theta. So the position variation are shown here. Now I'll show the design of the filter. Now this is the dual band stop filter. So where one open-ended stub with stepped impedance is used. In addition to that, there are two series elements, Z3, theta 3 also shown. So based on the method I explained, we can derive the S parameter. Just here it is not shown, but I'll explain. For any network can be thought as a cascaded transmission line section. Suppose Z3 theta 3 is cascaded to the open-ended line, and again that is cascaded with Z3 theta 3. So that here we can use comfortably the ABCD parameter to get the overall S parameters. Just by multiplying individual ABCD parameters, we will get the overall ABCD parameters, finally convert into S parameters. After that, this expression we will get. Now here in the next right diagram, we have added, since the series transmission line, the effect of series transmission line for improving the bandwidth, the effect on bandwidth is shown here. So as the Z3 increases, the bandwidth also increases. That means if the line becomes thinner in terms of microstrip physical dimension, we will have wider bandwidth. So this is the implemented filter as an example. So after finalizing the impedances, suppose Z3 is equal to 95 ohms and Z1 is equal to 35 ohms and Z2 is 70. So these are the selected values to get the responses at 1.5 and 3.5 as an example. The same structure is implemented in microstrip, and for miniaturization we can bend the transmission lines also, and we should compensate all this bending and whatever junctions used. Accordingly, if we see the EM simulation response and measured response are very well matched. So this is an example just designed for at some frequencies. Other example I am showing here, where two open-ended transmission lines are used, one short-circuited coupled line is used in between. As I told, for the short-ended coupled line also ABCD parameters are available, and we can multiply the stub ABCD parameters and again this and again one more stub impedance. If we multiply those, we'll get overall S parameters like this, and we'll see a dual stop band response with sharp transitions compared to the previous one. Since here only one stub is used, we are getting little gradual response. Here, very sharp transition, and deep suppression also we are seeing two stop bands. And here also that even mode impedance effect on the bandwidth we can study. So these are just one example. This is designed for the mobile bands, 0.9 gigahertz and 2.1 gigahertz. So the same structure is implemented in microchip. It is a basic FR4 substrate, commercially available at 4.3 epsilon, and thickness is 1.6 mm. So there is a deviation we can see here. I want to show the effect of the couple line from the ideal response to the practical response. So ideally, we assumed there is an equal phase velocities in that one, like even mode, odd mode phase velocities are same. But practically, depending on the substrate epsilon, those will not be same. That's why you will get some deviation in terms of the transmission zeros in the mid band. If you see, that is not as expected in the theoretical simulation. So the EM simulation itself shows the deviation followed by the measurement if your design is properly simulated. But however, if the rejection levels are well meeting, we need not to bother about the transmission zero shape. So we can go ahead. Next, so far I have shown dual band stop responses. Now we'll see how the ultra wideband band stop response is achieved. In the very first slide I have shown a conventional filter is having a narrow, simple one stop band. If two transmission zeros are introduced, that stop band width increases drastically. At the same time, filter roll-off also becomes sharper. So here, as a first one, I have shown the top one is conventional optimum band stop filter. Optimum band stop filter is termed because with 3 stubs, we can have comfortably the widest response. That's why they are called, it is an optimum band stop filter. Like that, n number of stubs we can use. So if we take the optimum band stop filter response, it is producing a single transmission zero like any other, but with sharp rejection. Now, if we incorporate the stepped impedance line in between, then as we know, the stepped impedance stub with impedance ratio, impedance selection will have 2 more stop bands. That's why in addition to the center stop band, we'll see 2 more transmission zeros, just lower side and higher side, which results in an ultra wideband band stop filter response. Here, more than 120% stop band bandwidth is achieved. Now the bandwidth and roll-off, everything controlled by just varying the impedances only. Everything we can predict here. The controllability of the 2 stop transmission zeros and above and below the stop band. At the same time, the roll-off and the rejection depth also, everything we can control with the impedances. Now how this is generated, just I have shown. The step impedance stub with 2 transmission zeros, and the 2 more stubs at the ends will produce 0 at 1 gigahertz, so that 1, 2, 3 transmission zeros are observed. So for this, we can derive the ABCD parameters. It is just a bit lengthy derivation, but if we are using MATLAB, we don't need to derive, just we can give the parameters as a multiplication, that's all. After that, if you want to see the positions of the transmission zeros, then simply substitute S21 is equal to 0. After getting the final S parameter, we can have, see here, S parameters are not derived, just shown in terms of ABCD. So now the implementation on microchip. So the same circuit here, the higher impedance, the open stub, at the end it is using low impedance line, ZL, that will occupy little wider width on microchip. Instead of that, we can replace that ZL with a combination of 2 parallel lines that is implemented here. So a single low impedance line is replaced with a parallel combination of 2 high impedance for miniaturization purpose. And the geometry selection we can have as compact as possible. That depends on the designer's choice. Now, if you see all the 3 responses in the here right side, so these are almost followed the circuit simulation except the very out of band response. Like that ultra wide stop band with roll off, everything is almost achieved. While in the out of band, because the geometry is made in such a way all lines became closer, so there will be coupling effects also. So that's why the return loss in the out of band is not as per the circuit simulation, but the trend is same. And the levels are since below 20 dB, it is optimized and stopped at that extent. So here, this is the ultra wideband so far available in literature, 122% stop band bandwidth. and the sharp roll-offs are major part of this one. So this same filter can also be thought as a low-pass filter because the wide stop band is there. So it is ultra wideband band stop filter or a low-pass filter with wide stop. Now, so far we used only transmission line and one coupled line used. Now here, entirely using coupled lines, one example is shown. This is called coupled line hairpin unit, where an end-shorted line and open-ended coupled line are constructed in the form of a hairpin. So for that, just how to derive the responses means, suppose if we take the input on output as a reference, below that is a open-ended coupled line. For that, Y parameters are available, and above short-ended coupled line, for that Y parameters are available. Just by adding the two Y parameters, because these two are parallelly connected, so we'll get a overall Y parameter. For that, just using the conversion formula, we'll get the S parameters like that. So this will produce a wide stop band response with 3 transmission zeros. In the right side, it is shown S21 response is shown. So again, depending on here, the beauty is only 2 parameters, ZY, ZO. For the entire filter design, only 2 parameters are controlling the stop band bandwidth, stop band depth, and everything. So as an example, it is shown for ZY, ZO ratio is fixed here as 2.5. Though the ratio is fixed, we can have different values like 140, 125, all the ratio remains same. But what is observed is the stop band rejection depth is slightly varying, but the matching, the return loss response in the out of band is significantly varying. So accordingly, the designer can select the impedances here. Next, this filter, as I mentioned earlier about the harmonic responses, the same response will be repeated at odd harmonics. So that is shown in this one. That means at 1 GHz, if we design the 3 transmission zero set will repeat at 3 GHz. In between, there will be a pass band. Now, if you construct an open-ended stub and select the electrical line such a way that it will produce a transmission zero at 2 GHz, we'll see a continuous stop band starting from 1 GHz to 3 GHz. So with the simple addition of a stub at the input and output and its electrical length, if we select in such a way that so that we are drastically changing the behavior, we are converting the simple band stop filter into a low pass filter with wider stop band. So that is the extension of that one. So here the variation, the effect of the stub impedance is shown here. As the stub impedance increases, the 35, 50, 60, we are just simulated. And we are seeing the rejection suppression level is varying in that way. So that we can select comfortably if the overall parameters are less than 20 dB, that is of IEEE standard. If the stop band rejection is 20 dB, that is good enough. We can go ahead with the design. So we can then, once if we finalize the circuit part, and we can predict the design here itself, then only we can go for EM simulation. So here the final filter is implemented like this. The value is selected for a 20 dB stop band rejection are even mode impedance 128 ohm and 55. At the same time, the designer has to keep in mind that whether the impedances are realizable for practical implementation. Suppose a particular combination of even and odd mode impedances are giving a 0.1 mm line, then we will not select that one because it's very difficult to realize practically. So at the same time, every time what substrate we are using, whether these values are implementable there also, we should consider. So this is the response. And where the circuit simulation response is shown as a dotted, it is well below the 20 dB. Since the couple line is used, and because the couple line practical implementation is different from theoretical, that's why we are getting the deviation. However, if it is below 20 dB, so that is acceptable. Whereas the filter roll-offs are almost followed the circuit simulation. And one more example using a stepped impedance hairpin unit compared to the simple micro coupled line hairpin unit. Here a combination of again a transmission line and a coupled line is used. So I'll move fast. So here, while selecting the electrical length for the coupled line set, that quarter wave length electrical length, and for that lower transmission line, the theta 2 is pi, that is 180 degree. then we will get a band stop with 3 transmission zeros. So same derivation we can have again y parameters for transmission line and coupled line. Just add those and convert into S parameters. We'll get the overall. And finally, this is the implementation. So compared to the previous one with entirely coupled line, here we'll get some our measured response is close to, because one transmission line is also used. So finally, compared geometry selection is the art by the designer's choice. How nicely you can have the geometry within small size. Now extending this band stop filter into low pass. Here earlier I have shown by connecting 2 stubs simply. Here one method is to design another low pass filter at the mid band. Suppose at 1 GHz if we design, the same set will repeat at 3 GHz. In between at 2 GHz if we design a smallest low pass filter, and if these two can be cascaded, then you will get a wider stop band low pass filter with high rejection compared to the simple stub used. Because the stub is a small element there, then we will not get the high rejection. Instead of that, we can add one more low pass filter so that we will get deeper rejection. So 2 examples are shown here. So 2 units are cascaded with a simple transmission line in between, and the impedance selection also to get the match that the 3 value also you can control, so that the overall level should be less than 30 dB or 20 dB and wider stop. These are just examples. Now one more band stop filter entirely using coupled lines in this fashion. So this will also, this is the here I need to mention the whole filter size in terms of width is smaller than a 50 ohm line. So because 2 coupled lines are connected in terms of H, in the form of H, the even mode odd mode impedance are selected such a way that the entire width is smaller than a 50 ohm line. 50 ohm line means on microstrip FR4 substrate it is occupying 3 mm. So here the entire filter width is less than 3 mm. So any filter can be thought of as a construction of transmission component, but here entire filter is completed simply as good as a simple line, and it is also producing a very good response with 30 dB rejection and sharp roll off. So these will be of highly interested if we integrate with an antenna without using much circuit area and without having a complicated analysis. Simply by understanding the behavior, we can add this in for the antenna harmonic separation pointer. I'll show that example also. Here, one beauty is earlier example I have shown 2 filters are cascaded using a transmission line in between. Otherwise, it is difficult to add these two, join these two. But here, this configuration allows to cascade a small low pass filter just at the other port, as shown in the circuit. So the first top filter is designed at 1 GHz. The same set is repeating at 3 GHz. The smallest one is designed, the small H is designed at 2 GHz. And simply cascade these two without any transmission line. Then we will get a wide stop band up to 3.5 GHz. So this is implemented in microstrip form like this. So far, some examples I have discussed based on coupled lines, transmission lines, and their topology arrangement. Now, one more class is, that is signal interference concept, where multiple transmission line sections are connected in parallel so that a complete closed loop will be used. That means we can have different electrical lengths for different lines so that the signal passes in multiple paths from input to output. Whenever a constructive interference happens at the output, we'll see a pass band. Whenever a destructive interference, depending on the electrical length and impedances happens, we'll see a stop band. So this is the concept published in IIT MAP. So here a simple 2 transmission line connection in this loop form, and we can derive the S parameter simply by adding the Y parameters of one transmission line, again Y parameters of other one with different length. We'll get S parameter. Now, based on the selection, if theta 1 is 90 degree and theta 2 is 270 degree, we'll get a band stop response with two transmission zeros. If the impedances are same, then we'll have one stop band only. If the impedances are different, again we'll have two transmission zeros above and below, so that the bandwidth gets little widened and sharp roll-off can be achieved. And similarly, the same response, band stop response, will be achieved when theta 1 is 180 degree and 360 degree also. That is not shown here, where you will have two more transmission zeros with single middle transmission. Total three transmission zeros will be achieved. And here band stop example is shown. Similarly, in literature, the same signal interference concept is there for band pass filters and dual band pass filters also. In next example, signal interference concept using coupled line. So compared to just this design, it is having narrow stop band response. Here, the Z1 theta 1, if it is replaced with a coupled line with open ends, then we'll see a wider stop band response with multiple transmission zeros, depending on the parameters, like ZO, ZO. So here, there is a possibility to get 3 transmission zeros and 4 transmission zeros and 2 transmission zeros also. Obviously, if it is a 3 transmission zero unit, the filter ripple remains constant. If it is a 4 transmission zero filter, then we'll need to have some more adjustment to get all that ripple level remains same. So that is little difficult. So these are all based on selection of impedances only. So after having the derivation and see the controllability and all, we concluded when the impedance ratio is 3, ZY 3, and accordingly the stub impedance selection will have a 3 transmission zeros comfortably. So for this is the derivation, and this is the implementation. So the couple line with the transmission line impedance is little low, that's why a wider line is shown bottom. Now so far we have seen band stop and low pass filter. Now few examples for band pass will show. So here a cascaded version of n number of couple lines is shown here. This is the first textbook design. As if single unit is used, we will see a gradual pass band from pass band to stop band transition, and as the number of sections increases, the filter roll-off becomes sharp. And at the same time, theoretically it is okay. Practically, we will see a little higher insertion loss. But here, simply instead of having a general opinion of just cascade filters will give high loss like that, we can also study the behavior and in terms of return loss also, not only insertion loss, how the return loss varies. Sometimes return loss is as wide as enough so that the entire pass band will have very good matching. So if these can be used for antenna harmonic suppression purpose also, because if the antenna fundamental frequency is passed by this filter, and the out of band will always that antenna response also follows the filter response. That means in terms of gain. So out of band we can suppress the gain. So that advantage we can take with this type of filter. And compared to the conventional filter, a couple line with two open-ended stubs of half wavelength. Earlier I have shown half wavelength stubs will produce a fixed zeros at 0.5 and 1.5. We have taken that advantage, whereas the in-between pass band of the couple line is not affected. Simply two transmission zeros created so that the pass band to stop band transition became very sharp. And the same set repeats at other multiples. So this way we can have a wideband pass band response or narrow band or ultra wideband also. And one more example, coupled line with stepped impedance stub, where we'll have a controllability in the out of band transmission zeros. So this example, just one plot is shown to understand. The dotted portion of green line shows that double section open stub, where at 0.5 and 1 above 1.5 two stop bands are there. Whereas the couple line simply gives a pass band, that is a black line. Now the combination of these two gives the first starting from DC, and it follows that first transmission zero, again pass band, again second transmission zero. So this is the behavior. We can easily derive its S parameters also. This is the practical implementation. Now, shall we give a break, madam? 5 minutes.
Okay, so then we'll take a 5 minutes break.
Then I'll go ahead with the other applications. Otherwise, at a stretch, it may get bored.
Okay, sir, sure.
Yes.
So, dear participants, now we'll take a break for 5 minutes. We'll resume this session at 11:15.
Hello?
Madam,
Yes, sir.
shall we start, madam? Just you ask to
Sure,
start.
sir.
Yes,
Wa-
yes, madam, I am there, madam.
Okay,
Shall,
then we shall start it, sir.
okay, madam, sure.
Okay.
Okay. So, welcome back. Now, so far we have discussed about the transmission line topologies which are giving different filter responses. Now we'll see, first we'll complete the antenna application. After that, some RF front-end applications I'll explain. Now that what here I'm going to highlight is the filtering antenna. Now this is a almost evolved research topic where filter is the integral part of the antenna instead of connecting antenna and filter separately with cable. Suppose if it is satellite application, that antenna will be located at some outer body of the satellite, and the filter will be inside the subsystem, so that a long cable will go and connect that antenna and the filter or a subsystem, so which makes the system bulkier and additional losses in terms of cable losses, bending losses, so many other factors also will be incorporated here. So instead of that, if a filter is a part of the antenna, so that antenna performance, individual performance characteristics can be improved. At the same time, suppose if two small subsystems are close by, suppose that 2 gigahertz and 2.2 gigahertz, such a way that suppose for L-band application, L1, L5 frequencies like 1.2 gigahertz and 1.5 gigahertz application. So the dual band application where that one antenna can be used if it is a wideband antenna, but two subsystems will share the common antenna. And at the same time, one antenna gain should not be even good at other frequency. In such applications, if we incorporate in the part as a part of antenna, so that we'll gain the advantage in terms of the gain and out of band responses. So for that, just this filter for two applications I'm showing here. So usually these will be connected with a cable, but we are using as a part of the antenna. So first of all, harmonic suppression, harmonic radiations in microstrip, simple microstrip patch antenna. There is no much new design in patch antenna. We can apply the same concept to advanced antennas also with different shapes and different circular population, other antennas. One traditional microchip patch is taken. We'll use the filtering concept to reduce the multiple harmonic radiation. But here what is to be highlighted is, for this usually there are methods available in terms of multi-layer and defected ground plane structure, suppose. Because the bottom ground plane of the antenna will be etched in such a way that the out of band radiation, that means higher order all harmonics will be suppressed. So these all designs are bit tedious. These all to be we should depend on the EM simulators only. And finally, the placement of the antenna, because in the bottom also, if we have some structure, we cannot place the antenna on a plane or any boom. So we should leave some air space, volume below the antenna, so that the bottom structure also electromagnetically should perform well. So these are all the complications if we use defected ground structures or metamaterial based structures, where other designs also available in the ground plane. Instead of that, if a uniplanar design comfortably in the same antenna plane, if you are able to design any filter so that it is not disturbing the antenna much, and but improving the characteristics like suppressing the out of band, these are of great importance. So for that purpose, just a simple insert feed antenna is designed at 2.4 gigahertz. And if we see the out of band responses, just the first two higher order modes are shown at 4.5 and 5.8 gigahertz. For this, to suppress those harmonics, here an optimum bandstop filter, earlier in my slides I have shown for bandstop filter. So a simple 3-stub unit is taken, so that the main idea is to suppress the out of band harmonics only. That means that low pass filter response should have a pass band which should cover the antenna fundamental frequency, and it should have a stop band as wide as possible. So for that, here, since the 3-stub unit technically after deriving, we have that middle stub impedance is low, that is that will occupy a little larger width or microstrip. Instead of using the low impedance line, we can just replace all low impedance lines with their parallel combination of two impedances. Just double the impedance, that's all. So that the overall area looks very small using thinner line. So without degradation of much performance. The circuit point of view, the response of these two remains same. But EM simulation, we have to see that it should have minimal effect compared to that reference design. So this is the implementation in microstrip. The impedance values are selected such a way that horizontal line impedance is 120 ohms and vertical sub. Middle one is having low impedance. That means a parallel combination of 60 ohms. That means ideally Z3 is 30 ohms only. So it is replaced with 260 ohm lines. Similarly, end stubs are having some 80 ohm and 50 plus ohm. That's why it is replaced with 116 ohm. So the response of this is, it is passing the 2.4 gigahertz, and the return was also very good at that 2.4 gigahertz. And out of band, this is the response of the low pass filter. Now this is integrated at the feed line of the antenna. So here, where to integrate the filter, that is a bit tricky thing. So after few simulations, EM simulations only, because antenna cannot be implemented in the circuit simulation. Then what is observed is from the antenna edge, after quarter wavelength line, if we add the filter, then there is a minimal effect of the filter on the antenna fundamental return loss. Otherwise, if the filter becomes close to the antenna, so the antenna parameter also disturbed. So that's why after quarter wavelength line on this for substrate, it is around 16.8 mm. The filter is straightforward cascaded on the feed line. So the bottom layer, bottom plane remains ground only. We have nothing to do with that. Simply adding the filter at the feed line. So compared to the antenna out of band responses at 4.5 and 6 gigahertz, since these are suppressed by the low pass filter out of band response, so we'll see a clean suppression of these first two higher order modes. So this is just an example. Now, as I have shown in the previous low pass filter, there is a widest stop band filter where up to 10 times there is no stop band, 10 times the cutoff frequency. If you use such a filter, you will gain some more advantages. That means some more harmonics of the antenna also get suppressed. So this is the measured response showing the reference antenna and the filter now where the filter is integrated. So the first two higher order modes suppressed. After that, other modes remain same. Almost they are repeating. Whereas the fundamental resonance frequency remains affected, and it is as good as the reference antenna. So if you see the narrow band response, this is good with a small minor frequency shift of around some few megahertz only. Whereas the 10 dB return loss bandwidth remains same. And if we compare the patterns also, now one point is to be mentioned in terms of gain of the antenna. Suppose the reference antenna gain is 4.5 dB here. Since the low pass filter is having around 1.2 dB loss in the insertion loss point of view, the filter loss straightforward contribute to the gain only. That means the gain of the antenna will be reduced by that amount of loss of the filter. So if that gain is acceptable, so the designer has to select such a way that the antenna gain should be made, or within that margin we have to design the filter loss. Otherwise, we'll get the advantage in both in out of band suppression, where all fundamental parameters remains affected except the gain. So this is one example for harmonic suppression. Other one is to have gain reduction at unwanted frequency. So here I cannot show the application in pictorial point of view, but I'll explain. For example, if you take the satellite Chandrayaan application, there is a lander and rover. So the lander will land on the moon or any other planet. If the rover is, the frequencies are selected such a way that those who are close by, suppose at 200 megahertz away hardly. If it is one is at 2 gigahertz, other is at 2.2 gigahertz. So that one system should not be affected by other one because these two are close by. That means one transmitter should, if it is closely spaced by the receiver, at other frequency, that signal should not be picked up by this one. For that purpose, we should have antenna gain, one antenna gain. If it is designed at 2 GHz, that should have, if you practically measure, we will see a considerable amount of gain at other 200 megahertz. If you see the frequency plot, frequency versus gain. So that now, if the idea is, if we design a very good band pass filter, which will have a very good pass band at the required frequency and a very good suppression at other frequency, if that filter is integrated with the antenna, then the antenna gain also follows the same pattern. That is the biggest advantage is achieved. For that, here one example is shown, a microchip patch and a slot coupled patch antenna. It is designed at 2.4 GHz. Here, this dual mode band stop filter, band pass filter is shown here. So the filter type and responses, again, I'll go back and I'll show you. But the basic insertion loss response is like this. It is passing the 2.4 GHz and it is rejecting the 2.6 GHz, 200 MHz array by 50 dB. So, and the passband insertion loss around 1 dB. It is simulation, it is 1 dB. Practically, we'll get little more. So this will be straightforward add to the gain of the antenna at fundamental frequency, whereas the gain at the out of band reduces and follows this filter response. So that is observed here. Now the simulation, the EM simulation response of individual antenna and the filter cascade. As I mentioned, the filter is cascaded at quarter wavelength away from the antenna edge. So that since the filter return loss is below 20 dB in this fashion, we'll see the overall return loss range where the antenna fundamental resonance remains almost same with the same bandwidth and all. Now this is the plot showing copole and cross pole for the reference antenna and the proposed antenna. So the gain of the antenna at fundamental frequency is 4.2 dB. At other frequency it is minus 7 dB is observed for the slot coupled patch antenna. Where after integrating the filter, it is around 45 dB it is suppressed and the gain reduced to 3 dB. That means 1.2 dB. That filter loss is added here. So, but out of band gain drastically reduced, whereas the copole cross pole pattern remains same. So this is just one-to-one comparison of only reference antenna and antenna with filter. And this is the gain plot comparing the single antenna and antenna with filter. So the gain pattern followed by the band pass filter. So in this way we can add some filters for antenna. It should be a part of antenna so that we'll gain some advantage. So these are the antenna applications, just two I'm showing quickly where the transmission line filters are used. Now I'll go back to the filter. This filter, this is used for antenna cascading purpose there. So here I'll just explain this. I'll come to front end application. So the diplexer I'm going to highlight here. So high rejection microchip diplexer for RF front end. So just a quick introduction for the diplexer. The diplexer is a combination of two filters basically, where the transmitter and receiver are connected to that one, so that a common antenna shared by the transmitter and receiver. So since if the antenna is wideband, so that transmitter should not, the receiver should not be saturated by the high powers of transmitter. That means there should be a very good isolation between the transmitter and receiver. So what is doing that job is this diplexer. So where the transmit and receive filters are designed to have low loss and high rejection, so that the transmit filter will have a very high rejection at low receiver frequencies. Usually, depending on the application, we'll select the technology. Most of the satellite applications require waveguide filters only to meet the high rejection. And wherever possible, if the rejections are not so stringent, we can go with microchip designs also. So for this, again, I'm coming back to the filters. What type of filter is suitable for this? If it is a planar filter version, because conventional filters will not have high rejection with the smaller sections. At the same time, they will have larger losses. Then here I'll introduce some asymmetric frequency response filters. So for that, just a diplexer basic response I'm showing. It is a 3-port network. Since S21 and S31 are the filter responses, S23 becomes the isolation, and S11 will become the return loss, obviously. So Here we should not get confused with a duplexer. There is a terminology difference, diplexer and duplexer. Mostly here, a diplexer, the fundamental difference is diplexer will have two different frequencies. Whereas in duplexing operation, we'll have the same frequency only. But that means transmitter and receiver, mostly in radar application, transmitter and receiver will have the same frequency. When it is transmitting, the receiver will be shut off. So all the selection will be done there by using a switch. So that switch provides a very good isolation there. That means in receiving mode, transmitter will be isolated like that there. But here in diplexer, two different frequencies, transmit frequency and receive frequency will be different. So that one should have higher rejection at other frequency. That is the challenge in the filter with low loss. Now for this, a new class of filters, those are called dual mode open loop resonators. Here the geometry wise it is shown like that. Where again in our transmission line model, we can give the equivalent model like this, where the input is coupled to that in between element, that is the dual mode open loop resonator, where a simple transmission line of half wavelength is connected in a C-shaped form. In between, a stepped impedance open stub is loaded. So that if we see the EM analysis, the mode split happens to get a passband with asymmetric type of response. That means a transmission zero is produced on higher side of the passband or lower side of the passband, depending on the geometrical parameters. So one part is explaining the structure based on the mode theory. That means current distribution and even mode, odd mode distribution in the field form. We need a EM simulator for that. Instead of that, if we are able to replace with the transmission line element and start deriving the parameters and control the transmission zero depending on simply selecting the impedances, then it is easy to have when the transmission zero comes on right side of the zero and higher side, lower side of the center frequency. Here, why it is shown, why it is of much interest is, if the same type of filter is used for the diplexing application, we need not to have two symmetrical passbands. The lower side passband response will have an asymmetric response like shown here. That means it will have sharp roll-off at that means the transmit zero produced at the receive frequency, say it is at higher frequency. Similarly, that receive filter need not to be symmetric. So the main advantage is with this, it is called dual mode because, for example, if it is to be constructed using a conventional filter, there is a need for n resonators to achieve the same response and same rejection. But here we are getting with n half number of resonators. So that the loss becomes very important. I mean, considerable amount of improvement will be there in loss. That means we are using half number of resonators to get the similar type of response. So that's why these are of great importance. Low loss with sharp roll off and good rejection is simultaneously achieved. So these two types of filters, if cascaded, what happens? That is the attempt is shown here. So to get higher resonance, a higher depth of suppression, two units are cascaded instead of single unit is shown here. Single unit suppose gives a 15 dB rejection in the out of band. A double unit with the help of again a connecting line in between, it gives higher resistance as good as 30 dB. Similarly, a sharp roll of asymmetric response where the transmission zero in the left side of the fundamental frequency, or if it is a receive frequency, it is at 2.6 GHz, one is at 2.2 GHz. Like the 200 MHz away, we can have two different filters. So one is rejecting other frequency by 30 dB level. Now these two should be cascaded using appropriately designed common junction. That is important here in the diplexer design. So the individual filters are designed here at 2.07 and 2.3 GHz, usually 2.1 and 2.25. So that is the required frequency, but it is center frequencies are noted here. Now the appropriately designed junction can be a simple T junction. So here, since the two designs are those are providing the flexibility to use a common junction of same 50 ohm line, whereas the output lines, because couple lines are very thin, so those are directly joined to the 50 ohm line. That port 1 is the line is having 50 ohm line. So this geometry is allowed like this. Not all geometries this is the junction. So always the junction should be a T junction where the T junction is designed such a way that it should not disturb the individual passband responses. So we have to select the T arms such a way that one filter response should not be affected by other. So here this design, if you see the current distribution at lower frequency side, lower filter, so it is passing that first pass band is not disturbed. That means it is having maximum current distribution. Whereas other frequency it is that one. Now this is the response of the filter and implementation on RT derived 6010 substrate here. Epsilon is 10.2. So this is a simulated response and this is a measured response. So again, there is slight deviation in the second pass band for the measured response here. And this depends on the fabrication tolerances and the implementation and other substrate parameters, the epsilon dielectric constant variation practically. Not all substrate will give as good as your EM circuit simulation response. So our experience, to the extent possible, we can use articulated private exo substrate. That is very good substrate where the practical repeatability will be very good. This is just an example. So these are the dual mode filter, new class of filters where we can use in the front end for isolating the transmitter and receiver. Now antenna applications and diplexer application we completed. Now I'll show how the filtering concepts can be applied to improve and miniaturize the circuit components like branch line, rat race hybrids or balance here. So here just a rat race coupler is taken as an example. A fundamental frequency response and its out of band response are shown here. Now, since that basic design is constructed using 6 quadrivalent transmission lines, though we see the ring form in the textbook, so it is a combination of 6 transmission lines connected in between the ports where the impedances are root 2 Z0, that means 70.7 ohm, and all are quadrivalent line at fundamental frequency. Now, if each transmission line is replaced by its equivalent bandstop or low pass filter unit, like in the antenna how we use that low pass filter to suppress the out of band responses, similar concept. So a single stub unit, 2 stub unit, 3 stub unit, whatever. Here we are going to replace, that means equivalent form. There in the antenna design, just we have used that low pass filter will pass the fundamental frequency of antenna, that's all. But here, since this rat race coupler is having a unique impedance, that means the filter you are going to replace also should have the same impedance. That means I am mentioning it equivalence we have to see. So for this purpose, suppose the T junction is selected, we should derive the equivalence between these two by using the ABCD parameters. So usually the ABCD parameters of the conventional transmission line are known. So that should be equivalent to the T-shaped line. That means suppose T-shaped, it is the cascaded version of Z1 and Z2 and Z1. You multiply the overall ABCD. Then derive the expression in terms of the unknown parameters. What will be the Z1 to get an equivalent of 70.7 ohm. So here one graph is shown. So after deriving the expression, we'll have the variation of the impedances with respect to the electrical line. So what is observed is a quadrivalent line can be comfortably replaced with as smallest line, 45-degree line also with 3 stubs or 2 stubs like this. So one example is shown here. So first one is top line is transmission line, that quadrivalent line. Now it is replaced with a 60-degree line. That means quadrivalent becomes 90-degree becomes 60-degree. And similarly, stub electrical length we can select so that the stub electrical length directly contributes to the harmonic suppression, out of band harmony, because that is the one which is giving the wider stub and select depending on the stub impedance selection. Here it is targeted for 10 harmonic suppression. All transmission lines are replaced with T units. 6 T units are used to construct the rat race coupler. So wherever possible, we can have meandering for miniaturization, so that the rat race fundamental frequency remains same So here, after miniaturization, the size is reduced up to 80%, more than 80% is reduced with the advantage of out-of-band suppression. Now, suppose if we replace the entire rat race coupler using 3-stub unit. Here, if we see compared to the T-shaped unit, like single-stub unit, here the overall transmission line length, theta 1 by 2, theta 1 by 2 is shown. Theta 1 by 2 is selected as 22.5 degree. That means overall theta 1 becomes 45. That means the quarter wave length becomes even lambda by 8. That means half of the line, the entire unit is even much smaller than the transmission line. If such unit is incorporated in the rat race coupler design, the overall rat race coupler shrinks to only 25% of the conventional design. So these are the measured responses where the fundamental frequency are of, though there is a deviation, the 15 dB return loss bandwidth or 20 dB return loss bandwidth you can have as a difference that we should meet. So the huge advantage is out of band suppression is achieved. So in this way, earlier I have shown the signal interference technique. So that will produce a band stop response. The same concept you can apply to the branch line coupler or rat race coupler. So here in the first diagram, the equivalence is shown, how the ABCD parameters of individual one, so that we can derive the relationship between that new line and the conventional transmission line. Accordingly, you will select a parameters to get a stop band response in the out of band. Now, replace all the transmission line equivalent with the signal interference line. Because this is a branch line coupler compared to rat race coupler, here the two impedances are involved. The horizontal line is 35 ohms, vertical line is 50 ohms. Accordingly, we have to replace this signal interference line, two set of lines. This is not to be confused with a coupled line. These are just two transmission lines, that's all. Now replaced by the equivalent, this becomes the branch line. So here it is shown the effect of the impedances and electrical length in the out of band response. So here in the left side diagram, there are 4 cases shown. In one case, it is showing 3 transmission zeros with wider stop band. So that case we can select where the impedances becomes, it is a case C, 99 ohms for the 35 ohm line and 140 ohms for the 50 ohm line. So if we construct the branch line coupler with such type of configuration, then if we see the out of band response, the 3 transmission zeros repeated, whereas the fundamental branch line coupler response remains unaffected. Now this is the implemented branch line coupler with the signal interference line. So here the geometry is made such a way that there should be a minimal coupling, though the lines are closely spaced, so that you can take help of the EM simulation, how best you can design and you can miniaturize and you can accommodate inside the ring of the one, so that outer space we need not to go, so that overall area is confined to within the branch line dimension. So this is the one of the application of signal interference concept to the branch line coupler. Yes, yes. Now I covered the filters and application to hybrid coupler and diplexer and antenna. So with this, now I'll conclude. So far, as a conclusion, transmission line concepts for filter design, just understanding the individual elements and how these can be applied to hybrid couplers or any transmission line based structures can be replaced if we have the knowledge of the individual elements and filter configuration. And we can make use of this further for any other antenna designs also, in antenna arrays also. One thing, so all these designs are simply based on transmission. There are no complicated EM analysis. So just I'm not criticizing any other design. This is one area, one part where the researcher can directly connect easily to the concept, so that they will get motivated and encouraged. After that, we can understand any other structure, I can say. We can comfortably understand the behavior of other structures. Right. Thank you very much.
Thank you, sir. So we have a discussion session now. So I encourage all the participants to take active part in the discussion. You can post your questions in the chat box. Um, Sir, we'll be sharing our screen for the questions.
Sure.
So can you stop sharing
Stop.
your screen so that we
Oh,
can share ours?
yes, madam.
Thank you.
Oh, it's nice that sir asked some questions. Are the
Vamsi sir.
filters? Yes, sir. I'm seeing Raghavan's ask question.
Vamsi sir.
Yes.
Our beloved that Ravindra Mishra sir is here, Sri.
Oh, very good morning, sir.
Good morning, Nancy.
Yes, sir.
Welcome,
Very
sir.
good.
Welcome, Ravindra Mishra sir.
Thank you, Professor Perumal.
Your blessing, sir.
How are you doing, Professor Mishra? This is
I
Sudhakar.
am fine. Yes, Dr. Rao, I'm fine.
Long time.
Long time, yes, long
So
time.
you're okay now, health-wise?
Health-wise, yes, okay, I can talk, I can make presentation, but it's
Yeah, very good. Very good. Good to hear that.
He is your alumnus, same alumnus. Nancy and you both are from IIT Kharagpur.
Yes,
Yeah.
sir. Yes, sir. Yes, sir.
Both
Yes,
are from IIT Kharagpur. One thing I noticed from Nancy's presentation,
yes, sir.
that
Please,
he is
sir.
a worthy student of his right. Professor Subramanian, the way he understands and explains, Nancy
Yes.
almost did that same thing.
Yes, sir. Thank you, sir. Yes, sir. Happy.
I'm very proud of you.
Yes, sir.
The
Thank
way
you.
you understood and presented.
Yes, sir.
I have one suggestion. If you
Yes, sir. Definitely. Sir. Please.
the antenna part you said about filter, there is another method of using that.
Yes, sir.
You might have seen this paper by Professor Ito. It came in 98 or 99. I
Okay.
don't remember exactly, 98, 99.
Okay.
MWCL paper,
Okay.
in which he feeds the antenna from both ends.
Oh, okay.
Right. Doing that, he filters out all the even components. All even harmonics are filtered out.
Oh, okay.
By feeding from both the sides.
Both the sides. Okay, sir.
From both the sides.
Uh-huh.
That is a very good method of filtering out even modes.
Oh, yes, sir.
Odd modes you have to then use filter, but even modes easily you can filter out that way.
Yes, I'll look into, sir. I'll definitely download that one. Ito paper. No? Okay.
Ito, yes, Professor Ito.
Okay, sir. Okay. Sir.
Otherwise, it was a very insightful presentation. It showed your understanding, your grip on the topic that you presented. It was very good. Thank you. I enjoyed it completely.
Thank you, sir. This is my third presentation, sir. So far, last time I've given it NIT Rourkela. So, getting opportunity now only. Actually, I have not given so many talks. After joining ISRO, this is the third one. So, I welcome any suggestions, sir, so that I can improve further, so that it can be better for readability and interest point of view. So,
Keep giving more talks.
Thank you, sir.
Keep giving more talks. That is the only way.
Yes, sir. Yes, sir. Thank you.
So shall we start with the question, sir?
Yeah, go ahead.
Vamsi, sir?
Yes, madam.
Can you see the question, sir?
Yes, madam.
Okay.
Raghavan sir's question. These filters are used in Chandrayaan, fabricated in ISRO, and what type of transmission lines are used mostly space applications? I'll explain one by one, madam.
Yes, sir. Yes.
Yes, sir, definitely. These dual mode filters are used in Chandrayaan, sir. But okay, I can orally tell anything. Particularly for lander and rover transmitter and receiver purpose only, we have used the planar transmission line filters because where the size and weight are is of a great constraint. So and also there is no much frequency interference compared to this ground to satellite communication on the moon. So the frequency selection was 2.4 and 2.6 gigahertz. That's why the receivers and transmitters for the pre-selection and image rejection application, particularly in receivers, I have used this dual mode filter, sir, where the low loss at 2.4 gigahertz suppose. At the same time, it gets rejected at 50 dB rejection level that we achieved. And for low loss purpose, we have selected that RT 5880 substrate, whose epsilon is 2.2, close to 8, so that it is very low loss substrate that I am telling. So that is one part in the receiver. Two filters for planar, this transmission line filter. This whatever dual mode filter I explained, the same thing, same kind of filter we use. Similarly, for orbiter to lander communication also, one diplexer is there. So in the diplexer purpose also, we used a single resonator dual mode filter, whereas the output filters again are again waveguide filters only. So where the T junction, common junction is used for the diplexer, we used a single resonator microstrip filter with the T shape, T junction only, followed by the two filters are waveguide filters only to get the high rejection. So that is one way. And other low frequencies purpose for the low pass, I mean for the receiver, after several down conversions, we'll get a low frequency around 10.7 megahertz like that. For that, we use LC type of filters. So the transmission line theory is not at all applicable there. So these are the variety of filters we used in Chandrayaan. And this transmission lines, what type of are used means, I mean for filter purpose is microstrip transmission line. For waveguide, mostly the iris filter and E-plane filters are used. And the cable point of view, there are low loss semi-rigid cables for routing between the antenna and the filter or subsystem. So that is Raghavan sir's question. Now Sudhakar Rao sir's question. Most of the satellite applications require high Q waveguide implementation with 80 dB, 120 dB rejection. Yes, yes. Yes, sir. Now for this purpose, iris coupled comb line filter are used, sir. To get, as you mentioned exactly, the requirement for Chandrayaan is 80 dB only. Whereas for other IRS applications, it is 110 dB rejection. Where a hat coupled type of comb line filter is used to miniaturize purpose. That's all. Hat coupling is used for miniaturization. So I have worked on, I got the opportunity to learn waveguide concepts also because my PhD work mostly on planar only. After joining ISRO, I enjoyed learning the waveguide filters. So I learned this comb line filters with iris coupling for further miniaturization. So exactly these type of filters are used for transmitter and transmitter side, where these high rejections are required. So what are the constraint parameters to be considered while considering the coupling of the microfilters at millimeter? Yes. Now I'm happy to answer this question also because now I collaborated with one of my friend in Global Foundries. So we worked on the same topologies because I have done internship at IBM Semiconductor Research Laboratory. Earlier it was SRDC. Now it is given to Global Foundries. So we implemented this coupled line filters and the stub-based filters at 60 gigahertz using 0.18 micrometer CMOS technology. There, what is our experience? This coupling becomes crucial as you mentioned, sir. So whereas depending on their fabrication feasibility, a 4 micron is the minimum gap is allowed their design rule check purpose. So we limited to that 4 micron. Otherwise we designed reverse with that coupled line with that 4 micron because though our theory demands the 2 micron gap for the coupled line also. So we are restricted to 4 micron so that instead of getting a very good roll-off, we'll get a gradual roll-off with transmission zeros separated. But we see the good repeatability as per the EM simulation. That is the happiest thing, sir. So I have published 3 papers we published in IEEE transactions on circuits and systems 2, TCAS 2. But in my next presentations, I thought of including those. That means comparing these microchip designs at low frequencies versus millimeter wave design. So definitely I'll show these in my next presentation, but I answered your question that coupling parameters constraints are based on the practical implementation we limited, otherwise we designed the filter. And we observed depending on the metal stack, that thickness also, like a thin substrate in microchip and thick substrate, how they affect. The similar types of experience we saw there. Though it is 0.18 micrometer technology, with different technologies with different metal stack thicknesses, the filter parameters also changing. If thicker dielectric is available, we are getting good filter response compared to thinner one. So there, compared to microstrip here, there the conductor losses, because the top layer is 4 micron thick. So sometimes in one technology, if it is 2 micron, we are seeing more conductor losses also in terms of passband loss. That's also observed at millimeter frequency. The fifth question, can we meander configuration for filter design? Yes, sir. If it is based on a transmission line filter just like this, if suppose a simple quarter wavelength line of some comfortable impedance 100 ohms is there, correspondingly it will occupy some 0.4, 0.5 mm on microchip, we can meander the line because it is simply transmission line behavior only that result in bandwidth of the filter. As one example I have shown for band stop filter. So we can meander the line to make the geometry compact. At the same time, we have to compensate for the junction discontinuities also. So we have to increase the length at least by 10% for overall length if we meander the structure. So quality factor of a filtering antenna. Oh, this question is new to me. Filtering antenna quality factor I have not seen, sir. It's a good part. I'll try to learn this one, because quality factor of filter we'll see, and same time after integrating to the antenna it is not checked, because it is no longer filter. I feel it will become a one port device again. But I'll look into this definitely. Interesting quality factor overall antenna, I think. But right now I cannot answer this question. Can we use fractal resonator configuration for multi-band microchip? Yeah, multi-band microchip filter like this stepped impedance stub, or a combination of coupled line and stepped impedance stub, or closed loop resonator filters also there. So fractal resonator is in a way taking a patch-based resonator and cutting that in some fashion, or a wide, longer length line meandering in terms of fractal. So this is, I think, instead of implementing that's concept-wise filter concept, it has nothing to do, I feel. So we'll take any multi-band filter configuration. In that, if you want to apply fractal geometry, we can apply. And patch-based resonators are there. Instead of using a closed loop resonator, a simple thicker patch, circular patch also with a perturbation inside. So that will give a dual mode type of response. There we can apply the fractal-based geometry for that patch. So we can see how filter response is varying. Maybe frequency shift is happening, or we can take the advantage of miniaturization also. If it is the shift is towards left side.
HOD madam, can I interject for the last 2 questions?
Yes.
Yes,
Yes,
if you
sir.
allow me,
Yes, sir, sure.
let me tell you what I think. The
Yes, sir.
quality factor is, you can easily find out it. 1
Yes,
upon Q. Q is the total quality factor, antenna and filter, if you are considering it.
Yes, sir.
1 upon Q is equal to 1 upon Q of filter plus 1 upon Q of antenna.
Oh,
That way
okay.
you can find your quality factor.
Oh, thank you, sir. I noted, sir. Noted.
Okay. And the second question is fractal.
Yes, sir.
Fractal, when you design a fractal usually,
Yes, sir.
the frequencies are almost log periodically separated. So
Okay.
if your filtering requires log periodic separation, then
Okay.
you can go for fractal resonator configuration.
Oh,
Otherwise,
okay. Log period. Okay, sir. Okay.
The frequency bands, the frequencies,
Ah.
they are log periodical. Frequency bands are log periodically separated.
Yes.
It will be
Okay.
multi-band, but they are log periodically separated. So
Okay.
unless you have a specific requirement of log periodic separation in your filter design, it is not a good idea to use it. But when it is log periodic separation, definitely you can go for factorization.
Okay, sir.
Thank you. This is what I wanted to say.
Thank you. And one more question: is there studies going on related to SAR and millimeter wave antenna? Sir, I have not designed any millimeter wave antenna so far, sir. Maybe somebody can answer, sir. No requirement for millimeter wave antenna so far. That's why I didn't get the opportunity to start that. But whereas filters we applied because it is my bread and butter.
I see millimeter wave antennas got rejuvenated because of vehicular applications.
Yes, sir.
That's the definition of millimeter wave antenna.
Yes, sir.
If you are using in a vehicular application, then there is no requirement of SAR. Therefore, SAR study in millimeter wave antennas are of not practical use, so there are very few studies. They are not of practical use. Where millimeter wave antennas, their deployment is in a different place, in a different context. So SAR study millimeter wave antenna is rare. Yes,
So this millimeter wave antenna, this SAR and other things have come because of the variable type of antennas. Here we really don't require such things to be used on the spacecraft side. So that is why that is not really relevant. So, and millimeter wave band, of course, the spacecraft has not started using that frequency yet. So it will come up. So when that comes, I think they will have a lot of systems coming here. So in the Indian space program, I think it will now coming up slowly. So
Yes,
apart
sir.
from this, Vamshi, I would like to say some of the high performance filters which we have, you could have
Yes,
given
sir.
some idea. See,
Sir, yes, sir.
you are given mostly on the transmission line side, plus these
Yes,
high
sir.
performance filters like basically the comb filters. And
Yes,
then
sir.
intermediate, we used to use a lot of microstrip filters with hairpin or parallel coupled,
Yes,
or
sir.
the hybrid mode filters, dual mode or etc. at for X band. So they are all
Yes.
high performance filter, which I think Dr.
Yes, sir.
Sudhakar was asking. So we had number of other high performance filters,
Sir,
and then
next.
also the E-plane filter, which was also extremely good.
Yes, sir. Yes, sir.
So
Definitely.
there are many such high performance filters which you possibly can include as a part of your lecture in a later stage. Okay.
Yes, sir. Yes, sir. Definitely, sir. Thank
That
you,
will
sir.
be a very good idea because they are all, each one is so unique.
Unique. Yes, sir. Yes.
As you know, each one is so unique, and it
Yes.
requires such a great effort to make that fine.
Yes, sir.
Isn't it?
Next presentation,
So
I'll
those high
present those.
performance filters, you can also add it as part of your.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Because every filter, you require a host of filters, not as you have already told. Even that IF filters, we used to use SAW filters. There are two SAW filters which are used.
Yes, sir.
But IF, first IF and second IF. First IF, one is at nearly 10.7, other one
Yes,
is at about 190 megahertz.
Yes, sir.
So what you can do is the gamut of filters which are there can be added at a later stage as a part of your this thing when you give. Okay.
Yes, sir. Yes, sir. Definitely.
Otherwise, it was a very, very nice presentation.
Yes, sir. Thank you, sir.
All the best.
Thank you, sir. Thank you.
I think when you, this is Sudhakar.
Sir, yes, sir.
Just another comment. When you design these filters for satellite applications,
Yes,
it's
sir.
not just the filtering. I think there are a lot of other constraints you need to consider. One
Yes.
is, of course, the high rejection you need between TXRX.
Yes, sir.
Second is the high power handling. The transmit goes sometimes 2 to 3 kilowatts.
Yeah, that is true.
Design these filters, you don't have much freedom. You have to make sure that you maintain the minimum gap so that you can handle the power.
Yes.
Other is we have to take into account the thermal effects quite a bit. because the passband moves around with temperature quite a bit actually. So when you design these, I think keep in mind that you have to design them over wideband. And the worst case, I believe, is PIM, passive intermodulation.
Correct.
So interface these with antenna elements, the waveguide interfaces. You have to make sure you provide the right pressure between the flanges.
Yes, sir.
So any loose, I think it will create passive intermod effects. So all these constraints make the high performance filters for satellites a bit difficult, but it can be done. All these things you need to consider at the same
Yes, sir.
time.
Yes,
So there are also different types of filters. Combline is one of them, but there are cavity filters. There are also other types of filters like iris filters, corrugated filters. So it depends on application and frequency band, etc. So
Yes, sir.
some more, I think, work is being done in the satellite industry. So I think probably ISRO is also doing something.
Yes, sir. Yes, sir. Actually,
As you told, the testing of filters, specifically the DTC filters which you use, they have to be qualified for both multiplacting. There's a very major test for which you require a very special setup to do it.
yes, sir.
So specifically when you have high power operations, suppose you are connecting a 20 watt, 5 watt TWT as SSPA or even this thing or even less than that, the multiplacting can occur based on the situation we have. So this multiplacting and this overall high power test is very essential for all the filters.
Yes, sir. Sir, then next presentation I will include only those satellite point of view, because this is just academic purpose. I only consider.
That's fine. That's fine. Whatever you have done is fine. Is very good from the academic point of view. But what I'm saying is, as a final, this thing can add 1 or 2 slides to show what sort of high performance filters are really resulting from these studies and further.
Yes, sir. Noted, sir. This I'll definitely make out a very good
presentation.
Thank you, sir.
Hello, this is Raghavan. I just want to add one comment. Dr. Vamsi's presentation was excellent as far as the exam point of view and other things are concerned. One more thing I want to tell for the sake of the participants. Today's afternoon speaker, Dr. M.K. Mandal and Dr. Vamsi, they were almost like colleagues in Kharagpur.
Yes, sir. I'm a student.
Okay. Not much difference. In any case, afternoon speaker, he had a direct, he was fortunate to work directly under KU. And you know, KU has contributed a lot for SIW. So participants should not miss to hear Dr. R.K. Mandal. Why I am telling is, I feel at least 10% of the participants are not knowing the value. After signing the attendance, they are leaving. I feel very bad about it. You cannot get any of the lectures right from what you had from 9 o'clock yesterday till the last session. I want the participants to realize the efforts put by the organizers. Thanks a lot. Thanks a lot.
Yes.
Sir, we have come to the end of this session. Thank you very much, Vamsi, sir. We are very thankful to you for sharing your valuable knowledge with us and for being with us today.
Thank you, Madam. I want to thank Sudhakar Rao sir and Raghavan sir and R.K. Mishra sir, and particularly Raghavan sir who suggested my name. And thanks for giving me this opportunity, sir. And I'll incorporate all the suggestions given by all starlets. So I'll definitely in my further future presentations, as Madhavan sir suggested, I'll incorporate some more details for future purpose, if any given opportunity.
Anyway, we all enjoyed.
Thank you, sir.
Surely we will come back to you, sir. We need your help also. Thank you, sir. Sir, thank you, Sudhakar sir and Raghavan sir, Vamsi sir, Mahadevan sir, Ravindra Mishra sir. Thank you so much, sir.
Thank you.
Thank you.
Okay.
Thank you all. As we have come to the end of the first session, let us now break up for lunch and meet again for the second session at 1:30 p.m. without fail. Thank you once again.
Thank you.
One, two, three.